Well, to be perfectly candid, I'm humbled, and I very much appreciate this invitation. I'm probably the least distinguished of the lectures, but it is a great honor to be here, and I'll say too, a privilege. It's been a wonderful experience for us to support the Navy, and what I'd like to do today is to kind of give you a little background, and then hopefully you'll have an appreciation a little bit of how we approach translational research. How do you get from the biophysics to naval operations? And hopefully you'll see some of the work that we're doing and understand that lighting is the answer to just about every question you could possibly pose. A little background on Lighting Research Center at Rensselaer. We're a center that actually is not on campus. We've outgrew campus many years ago. We're 95% funded from outside sources. I like to say we work for a living, but a lot of what we do is translational research. So we do basic research, but everything we do is pretty much aimed at trying to benefit society in some way, and our mission statement is to advance the effective use of light for society and the environment, and that's been with us for nearly 30 years. Our first ONR grant was a Young Investigator Award to Professor Mariana Figueroa, who now is the center director. I stepped down in July, and she has 3 R1s and has been very successful, and probably a note of pride for ONR, Young Investigator Award, to see someone has achieved that level of success. Among the projects we do, you can see on the right-hand side a wide range, and some of the signature ones. Back in '04, we designed and engineered all the interior lighting for Boeing's Dreamliner. That design's been carried over into all of their other aircraft. We do a lot with humans, but we also have an animal laboratory. We run mice and rats and design lighting systems for mice and rats. They're 3,000 times more sensitive to light than humans, so scaling becomes pretty critical. We're the only university on the planet that has a full photometric electrical laboratory, so we do independent testing for governments. Sweden, I'll be leaving on Sunday to go to Sweden, and we support their energy efficiency programs, Canada, the Philippines, and so on. And as part of the university, we have a graduate program, and every year we graduate 3 or 4 PhDs that then take up jobs in industry or government or private practice. Now, I mentioned that for me, the answer to every question is lighting. And I think you're familiar with Abraham Maslow's, if the only tool you have is a hammer, everything looks like a nail. But it even creeps into science. So it says once you have a collider, every problem looks like a particle. So what I'm going to do today is basically talk about the fact that there are many nails out there for which lighting and biophysics actually play, in my opinion, a very critical role. I want to, though, lead into this by telling you that it's probably the most profound change in lighting has been the development of solid-state lighting. And the reason is you have infinite control now, but the bridge between research, where you can control spectrum and amount and duration and so on, to practice is much shorter now. So the same technologies we use in research can immediately go into practice, and that is a big deal for a center like the Lighting Research Center. So in the old days, as my wife says, what's the big deal? You turn the lights on, you see, you turn them off, you don't. And that reflects to some extent the technology we had. We had daylight, of course. We have high pressure sodium, metal halide, fluorescent, and halogen sources. And what's really interesting, as these new technologies came online right after Edison invented the incandescent bulb, the family of lighting products just continued to grow. Nothing displaced any other technology. There were other niches and expansion, but LEDs has changed all that. LEDs now have changed literally every lighting technology that's out there. Now, what's interesting about it is you can make white light or narrowband light, which you couldn't really do without clumsy filters and things like that. But now you have an emission that's narrowband, and you can use light spectrum almost like a scalpel to begin to understand how biological systems respond to that. The other thing that's often forgotten is that solid-state devices are high frequency, tight control over timing, and this actually turns out to be a real benefit too if you want to enhance, for example, brake lights on automobiles, for example. The slow rise in incandescent is not as profoundly attention-getting as something that comes on and off very quickly. And if you look at this curve here, this shows you, as a function of years, the luminous efficacy, how much light you get per watt out of a light source. And what you can see right away is that solid-state lighting has really eclipsed, you'll excuse the reference to yesterday, every other technology. So every technology that found a place in the marketplace is now being displaced by solid-state lighting. But perhaps the most important thing, it has got profoundly cheap. You can now do these things at a lower cost than you used to be, and it is truly a disruptive technology. It has changed manufacturers. Used to have the big three, and now nearly anybody can build a lighting system to deliver value to society. So I say this as a preface to really what I want to talk mostly about is the biophysics of light. But you have to remember that what I'm going to talk about is not like brand new science, but the ability to translate the research into practice is what has changed dramatically, and it's largely because of solid-state lighting. Now, this is sort of the way we conceptualize how we approach problems. At the center is warfighter performance. We want him or her to be able to be at peak performance, particularly at critical times. Light has impacts on the visual system, and it has impacts on what we call non-visual systems. And each of those, broadly speaking, have two branches. One is what we call visual performance. How quickly, how accurately can you process information, and then the appearance. What does it look like? Are really two distinct channels, and I'll go into some details on that. Each has its own biophysical relationship to the amount, the spectrum, the distribution, timing, and duration of the light stimulus. I'm not going to talk about polarization here, but those 5 dimensions are your degrees of freedom that you can manipulate to understand how the visual system or the non-visual system is going to work, and then how are we going to convert that into a technology that serves the purpose that we hope for. And on the non-visual systems, we have really circadian phase shifting. As you go from one time zone to another, your biological clock has to retrain, and that's due to the light-dark cycle that is incident on the retina, not on the back of your head, and not exercise, not diet. It's the light-dark cycle that entrains you. And then there are alerting effects, and I'll talk about some, I think, groundbreaking stuff we're doing for the Navy now with regard to how can you use light in addition to cups of coffee, which of course is what keeps the Navy going. Now, I have to stop here because I think that it's important you understand that this technology, solid-state lighting, and the biophysics is held back by lighting standards. And I'm going to go through some of the things we have here. This is the photopic luminous efficiency function. This is how we measure light from 400 to 700 nanometers. And we're looking at the efficiency. What is the weighting function to the electromagnetic spectrum that then gets put into a light meter like you see there? Now that standard was developed in 1924, and I remind you that that was 3 years before Lindbergh crossed the Atlantic, to kind of give you a time reference. This function is what we use today in the Navy for every specification for lighting standards that we have. But biophysics has moved on since Lindbergh flew the Atlantic. There is a lot of science that has been developed, and now coupled with the technology that we have, I suggest it's high time for a revolution in the way we develop lighting systems to serve warfighters. So for me, my background's in biophysics, and this has been sort of bread and butter for me for 30 years. What you see here is not a monolithic detector at the back of your eyeball. This has a distinct architecture. The center, or the foveal receptors in the eye, are densely packed with cones. These are the daytime photoreceptors. And then about 20 times greater density of nighttime detectors, the rods that are in the peripheral retina. So you can't just put light willy-nilly on the retina and expect a common effect. One is designed for nighttime vision, one is designed for daytime vision. And the other point that becomes critical is that we have what's called an inverted retina. If you notice, the light comes from the bottom of this picture, and then before it reaches the photoreceptors, and then the neurons communicate back down that channel to the brain for processing. So optical fidelity turns out to be relatively poor. You would never buy a camera that had such poor optics and basically a diffuser in front of your image plane. So there's a lot of very important neural processing that goes on, which is often forgotten. I give a whole lecture on why the eye is not like a camera. You've probably heard that many times, but it's a very different process. Now, the retina, again, remembering that the retinal architecture differs, has 5 photoreceptors. Each of those converts photons into electrical signals. Each is spectrally tuned to a different part of the spectrum. So you have 3 cones, the long wavelength, middle wavelength, and short wavelength sensitive cones. You have rods, which are the nighttime receptor. And then you have one that's recently discovered, the intrinsically photosensitive retinal ganglion cell, which does not lie in the photoreceptor layer. It actually is more proximal to the brain than the photoreceptors. It plays an important role in circadian rhythms. It seems to play a role in vision as well, and there's discoveries still coming about that. But these are the photoreceptors you have to deal with. So if you're going to deliver optical radiation, you first of all need to know how these photoreceptors are going to convert those photons into neural signals. The other thing I want to have in a very broad brush, as you leave the retina, there are basically 3 wires. There's the M channel, which is the magnocellular. It's the one that tells you where it is, how fast you respond. It reaches the brain sooner, and then is processed by the parietal lobe. So there's a division of labor between where something might be. If you need to detect something, one part of your brain deals with detection, and then you have another channel that says, well, what is it? And those things begin to talk at the primary visual cortex, and the interactions of those become important. And they become important because no single job you're going to do in the Navy is just detection or just recognizing what it is. Whatever you're going to design has to recognize the different spectral, absolute, and temporal sensitivity of those different channels if you're going to come up with a technology that really works. And what becomes important, and I think that even in my field, people tend to forget, they think of the photoreceptors, but it's actually the channels that leave the retina to the brain that really govern how well we see or the non-visual effects. So these are not photoreceptor spectral sensitivities. These represent different channels leaving the retina to reach different parts of the brain where you have a segregated responsibility in the brain to process information. Then it gets integrated by reciprocal feedback to give you a holistic view of, say, this room or this presentation. But you can, from an applications point of view, if you understand how each of those channels are going to respond in spectral, temporal, and amount, you can then begin to optimize lighting systems for better performance. So here's one that actually our friend, the 1924 curve, is part of one of these channels, but it's only one. So this is what we call visual performance, which says, where is it? How quickly can I respond to it? So if you need to detect something in the periphery, for example, this is the system, this is the channel that tells you there's a bogey at 6 o'clock. That's the one it is. Then you have to turn your fovea and identify what it is, whether it's a friend or foe, for example. But this is your early warning system. It has to do with on-axis, but primarily off-axis vision to make those detections. And remember that, because as I talk about some of the technology we developed, that becomes a central part of the understanding of how you develop a system. Now this is a relatively recently discovered channel that deals with how bright it is. How bright is this room? You say, well, it's middle, whatever it is. The spectral sensitivity of this is very different than what your light meter reads. And what happens is, I don't know if this may be a little arcane, and I don't mean to be, But as people moved from high pressure sodium, the orange street lights, and replaced them with LEDs, people said, geez, these are bright. Why is it so bright? And the reason is they're using the wrong instrument to measure the brightness. And I'll talk about that as well. The one on the right represents how you go from low to high brightness. What is the transfer function to do that? And it depends on whether you're looking, as it turns out, at a light source, or you're looking at the contrast on your smartphone. Each of those has a different biophysical relationship. So reading print is a very different functional relationship than how bright is that searchlight, for example, that you're going to see, or landing light. Then finally, I'm going to talk about circadian rhythms. Well, not finally, but this is a non-visual channel. You have no conscious access to know where your biological clock is. All you get is symptoms. If you fly from here to Tokyo, you feel tired, a little malaise, you are going to be hungry at the wrong times, and so on. The clock that gets you in train to Tokyo time is governed by the spectral sensitivity of those blue and yellow curves, not your light meter. And to specify how we're going to get people adjusted to new time zones becomes a matter of understanding not only the spectral, but the absolute response, which is on the right curve. And to kind of give you a reference, you'll see that these vertical bars are in different hues. So the darkest gray represents, for example, where the circadian system is at nighttime, roadway lighting, for example, if you go out at night. And what you notice is the circadian system is blind to that. So earlier today, we were talking about, if you go to the bathroom, turn the lights on, is this going to disrupt your circadian system? The answer is no. The light levels are too low generally to do that. The next gray bar is what you get in your house, and you can see it's a pretty dark from a circadian point of view. You can see fine. And then the next light gray is about what it is in offices as we build them in this country. Now, I'll talk later about the General Service Administration, who we work with, to try to get those light levels up to points where circadian entrainment can take place in offices. And that's a really important part for the well-being, sleep, depression that impacts your run-of-the-mill office worker. And then the lightest is what you would get outdoors under a partial eclipse even. Now, I'm going to take a little bit more time to talk to you about color, because color is important in aviation primarily. We use color to tell pilots, this is an airport, this is a runway, this is a taxiway, and so on. Now, a lot of people, I'm not sure anybody in this room, but I confronted often, and I even heard a Nobel laureate give a talk, which was wrong, about how there is an intrinsic color in every wavelength. That is not true. You do not have wavelengths that have inherent color. So as my thesis advisor said, color is a pigment of your imagination. It's a computation you make in the retina and brain to give us our color perception. There is nothing inherent in the physical world that has anything to do with color. It's all a computation that goes on in the brain. What's interesting is it's trichromatic. There are 3 dimensions to color perception. And these classic experiments, you see someone looking in and they have what's called a bipartite field. On the lower part is a white light, for example. You can take a red, green, and blue primary on the other side of that bipartite field, and they will look indistinguishable to a human observer. You can calculate that, and this field called colorimetry has been part of neuroscience for a very, very long time. So it's 3-dimensional, but the 3 dimensions to kind of give the color appearance, on the spine is an achromatic. How much light do we have? And it is going thing from black, gray to white. But then you have what are called spectral opponent channels, and this is red versus green and yellow versus blue. You cannot see, for example, a reddish green. You cannot see a yellowish blue. You can see a reddish blue, which is purple, but you can only combine them as spectral opponent processes. And what you do if you stick a microelectrode into the first relay station out of the eye to the brain, you see 3 channels. You have the achromatic channel at the top, so if you go from 400 to 700 nanometers and you find out where is it most sensitive to a constant photon level, you'll see that it has a peak sensitivity in humans at about 555 nanometers, sort of a Gaussian function. That same light to a different channel will give you a hyperpolarizing or a depolarizing response. That's how you signal red or green to the brain. If it hyperpolarizes, you're going to get a green signal to the brain. If it depolarizes, same cell, it signals red. And the same thing is true with yellow and blue. So these three neural channels that have been identified since 1924 are ones that we now know are a physiological basis for this cartoon that we have here on the left. So what we have here is a general model, and the way I try to do it with my students, I try to put it in terms of balance scales and scales in general. So you have your bipartite field on the upper left, you have your cone spectral sensitivities, and then you have these neural channels. So these discs are the short wavelength, middle wavelength sensitive cones. The lines indicate how these are combined, and you have a blue, yellow, a red, green, and a white channel. So what the white channel does, basically, it just counts photons, spectrally weighted according to the function that's up in the upper right-hand curve. And then your red, green, and yellow, blue channel are looking at those photons and deciding, are they more green, are they more red, are they more blue, are they more yellow, by their spectral sensitivities. So white is when blue, yellow is in perfect balance, red, green's in perfect balance, and you're just counting achromatic photons on the one channel that is unidirectional. Yellow, on the other hand, not only do you count photons, but you also have tipped the scale. So the spectrum has moved to longer wavelengths and gives you a pure yellow, but the red, green is in perfect balance. So that is our perception of yellow. And orange occurs when you have the yellow and the red scales tipped in one direction. That is the way we see orange. Obviously, gross simplification, but I think you understand that it's not the photoreceptors, it's not inherent in the wavelengths, this is the computation that goes on in the brain to give us our perception of color. So why do I go through all this? Well, one of my favorite quotes is from George Eastman. If you can understand a process, you can control the alternatives. And so when now you're talking about, all right, well, I've got this technology, I've got this science, what does it mean to the Navy? So let's start with these visual effects. So with this background, as brief as it is, I want to tell you a little bit about how we approach some of the problems that have military relevance. So this is a project actually done for the Federal Aviation Administration, but they have very similar problems to the Navy aviators. So as you would approach a runway, the problem that pilots were reporting fairly commonly was they couldn't tell the difference between white and green. So they had the lights out adjacent to the runway, and they were confused about what is it that they're trying to see and so on. Well, if you go back to this basic model, where white is where everything's in balance, and green, as I got here at the bottom, is a heavily tipped in terms of the green. There's no ambiguity between a green light and a white light. But filtered incandescents could oscillate. They sometimes look a little green, sometimes a little white, you get a little dirt on them, and so what happened is you had an ambiguous signal to the pilot about what it is that constituted either white or green signals. So what we did as a study based upon the computation procedures that we did, we were able to demonstrate empirically, first of all, the confusion between white and incandescent lamps, which you see here on the left bars, and the green. And so what we were able to do is take the existing technology, be able to compute what the spectral conditions were, and then predict which ones were going to be green, which ones were going to be white, with what level of uncertainty. So that's now a new, for civil aviation, federal aviation standard based upon the work that we've done. I think that has direct relevance to landing lights for the Navy as well. The other thing that happens, and if you may recall, how bright something looks is also different than what your light meter is telling you. So the problem was the pilots would come for approach. Some had been replaced with LEDs, some had not, still had the incandescent, and they were not uniform in terms of their brightness. And so what happens is, and again, another confusing situation for a pilot is that what's going on here? Why do they not look uniform? And so they empirically had that finding. But what we were able to do, this is the spectral power distribution. This is the emission spectrum for a LED and for an incandescent lamp. And this is what the standards say. These two should be equal in terms of their brightness. But this is what the pilots are saying. And indeed, we were able to take that basic understanding of this neural channel, and that now begins to be able to predict these kinds of results, and now FAA can back off the amount of light that comes out of the LEDs to make them look uniformly bright with incandescent. So they now have a way to deal with this problem in a quantitative, predictable way. Now, the other thing we've done for the FAA, this is a remote airfield primarily designed for Alaska. The governor of Alaska, prior to Palin, said he wanted to open up Alaska to 24/7 operations. You don't get to birth babies at the same time that you can reach them to be able to do that. So he's promised to the Alaskan people was that they were going to open all these grass fields to air transport 24/7. Now, the problem, of course, is the way they were doing it, they were putting smudge spots on, they'd get their snowmobiles, turn the lights on, and then a pilot had to land. And I'm telling you, the fatality rate for commercial pilots in Alaska is like 1 in 35 crash, something like that. That's a remarkable statistic to me. I'm sure the Navy does much better than that. But the point was, power becomes critical. It's not like you have a generator in a remote place above the Arctic Circle. So you have to maximize the visibility and minimize the electrical power required to do that. So here is, let's going back a few years, but these are different LED lights. On the left-hand side, you see your reaction time. That becomes a measure of how well you see it. The faster you see it, the better you see it. And then this is the photopic intensity in log steps as you go through there. And what you see is kind of a mess. What color should we use? How do we pick that? What are we really trying to do here? Because each color has a different relationship, right? And again, all of those are evaluated by the current standards, which is the spectral weighting function on the right-hand side. So part of the work that we did prior to this study was to develop a computational procedure that managed to be able to predict all of those data with a single spectral weighting function. And again, that is now being used by the FAA and their specifications for remote airfield. And we not only specified the intensity, but the color and then the flicker rate, because these have to flash at a certain weight, and we linked them to GPS, and so they're all synchronized, for example. But the point is, you can't do this if you don't understand the basic process that goes on in the retina. Understanding that gives you the opportunity to not do trial and error, but to actually zero in on what it is you want to specify, and in this case, remote airfield lighting. Now, this is a problem I think that faces, this is a project we did with NSMRL in Groton, as well as the Coast Guard across the river, and they wanted to, for civilians, to replace these pyrotechnic flares. I'm told, and you probably know as well as I do, these are risky warning lights that you're going to have. This is one I think the Navy has as well. I believe that to be true. But what we did is, again, you start with basics, and you now look at, you want to flicker it because it's a more attention getting if it comes on and off. And so you have to design it that it flickers at a point at which you're maximally sensitive. As it turns out, under very low light levels shown by that blue curve, this is your peak sensitivity to flicker. And it also has to not be confused with police lights or fire on land, because they go at 1.5 hertz. These are 5 hertz. And if you look at what you're trying to do, the first thing you have to do, because you're unlikely to be looking at a vessel in distress, you have to detect it. And you're going to detect it off axis. It turns out that the retina is tuned to, as we call it, cyan here. But once you detected it, you have to look at it and identify it. And what you see, I hope you can see this light that's flashing on the horizon up there. It has a cyan flash to detect the off-axis detection. Then once the fovea goes to acquire it, it's seen as an amber light. It's a unique signature that can't be confused with anything else in maritime operations. So this, I hope, will not only be for civilian, but perhaps replacing those pyrotechnic flares for the military as well. If you understand the process, you can control the alternatives, and solid state lighting has provided us, we don't have to have filters anymore. We can actually have a device, low power, that allows you to begin to help in rescue operations. So that's among some of the projects we've done. I tried to pick a few that were, I thought, most relevant to the Navy. This is really a whole new field. Back when we started in this in the mid-90s, I thought it was kind of cute. Light sort of regulates circadian rhythms and so on. I've come to believe, and if you don't remember anything else, I'm going to say to you, remember that circadian rhythms is the platform for all biology. If you don't deal with circadian rhythms, fatigue, sleep, the kinds of things that you have in naval operations, you're going to have mistakes, and you have to come to grips with it. And the thing that controls circadian rhythms is the light-dark pattern, 24 hours. When you go to Mars, it's 24 and a half. We'll have another problem to deal with that, but the point is, here on Earth, circadian rhythms becomes absolutely critical. So every creature on the surface of Earth goes through circadian rhythms. It's the most highly conserved mechanism that you're going to find in biology. Whether you're nocturnal, you're a plant, you're a diurnal, human, everything goes through the kinds of rhythms we have illustrated here. So this is actually a study funded by Office of Naval Research, looking at different biomarkers on how they are synchronized, or at least phase relationships between different markers. So we have melatonin, cortisol, alpha amylase, which is the digestive enzyme. It also goes through a circadian pattern, and core body temperature. And what you see is the sleep-wake cycles. So melatonin should be rising just prior to your normal sleep time. So it isn't it's sleep per se, it is an anticipatory self-running mechanism that anticipates you're about to fall asleep, and indeed signals the body to change from Dr. Jekyll to Mr. Hyde. We have physiology for nighttime and daytime, and this is one of the primary signals that gets through that. So what can light do on this? Well, if I give light early in the morning, I can change the phase relationship in my melatonin rhythm. And that's obvious. People have done that for many years. But understanding then what light, what do you mean by light? What's the spectrum? What's the amount? What's the duration? It becomes the challenge we've tried to do. But again, to show you completely, you can bring it back again to that phase relationship by applying light at the time. So that will phase delay and you'll wake up later. So this works pretty well in a very predictable way, and we're certainly not the only people that have been studying that. The other thing that we can measure, and we have a full-time nurse that looks at blood plasma, saliva, urine, be able to apply light and then measure the graded response that you get for nocturnal melatonin synthesis. So think of this in terms of, if I change the spectrum and the amount, the timing, I can modulate the depth of that dip to come up with these spectral sensitivity functions that you see on the left, the yellow and the blue. Again, the black one is our current lighting recommendations. And then we've already explained to you what the transfer function is. Once you have that basic understanding, then you can begin to apply it to different applications. And remember, circadian rhythms is the platform of all biology. So if you don't understand this, it's going to be kind of a willy-nilly process. We have taken this and we put it into a technology. So we have a light sensor. If you'll forgive my pilot blindness pointer here. This is a light sensor that's calibrated in terms of the spectral and the absolute sensitivity. So you wear this, and then this is measuring your activity. So you have an input to the system that we're modeling. You have an output, which is when you're awake and when you're active. And then it talks to your phone. And this is actually a project funded by the Swedish government and by the US Army to develop this technology. But I wanted to show you the kinds of data you get. So here's a day shift person. This is the light pattern over a week, the blue, and this is the activity. And what you can see qualitatively, these are well coordinated. That means that qualitatively, at least, this person is very well entrained to a day shift work. If you look at a rotating shift nurse, for example, the input-output relationship has a lot of high frequencies in it. It has the phase relationships are not clear with regard to the light-dark pattern and the activity-rest pattern. This is a disrupted person, and we know that disruption leads to things like breast cancer, cardiovascular disease, type 2 diabetes, the list goes on when you have a disrupted pattern like this. Now, what we develop is a set of math which we call phasor analysis. So this is over the full week of a day shift person. You notice that this is their activity in black. This is their light exposure, and again, you see a coordination. But this is over a week's time what a rotating shift person. There is virtually no relationship between their activity and their light exposure pattern. These people are disrupted, and the way we quantify it is this vector, which we call a phaser. You should be in the first quadrant. The longer that vector, the more entrained you are. This is the rotating shift person, and you can see that it's a much shorter vector. So in terms of Navy operations, this is a project we did at sea. Colin Young was the physician on board while they went on duty. We first of all had to convince the admiral that move from an 18-hour to a 24-hour shift, because there's not much you can do on an 18-hour. You can't entrain to an 18-hour day, but you can to 24. And then we gave them bright light in the engine room. We were looking at the engineers that were in the propulsion room, and what you find is these people were less sleepy when you put them on this bright light during operations and darkness at night. They had their melatonin was synchronized with their sleep now, which is a good thing. Remember, you have to anticipate it. So being able to coordinate the melatonin rhythm with the sleep pattern. And then this is our phaser magnitude. And what you see is their activity rest period was much better coordinated with their light-dark pattern. So all of these point to biomarkers that allow you to quantify how impactful is the 24-hour shift coupled with higher light levels, by the way, than what you now have on submarines, in the engine room at least, to what you have here. We tend to have dim light levels because it's more energy efficient, but it's not good biologically. Now, this is another project funded by Office of Naval Research, and I'll go through it because I think it's interesting from an applications point of view. So this is your melatonin rhythm. When you're given, these people are awake 27 hours continuously. This is what your melatonin levels are under dark, and you have dark at night, so you go from daytime to nighttime. When you're exposed to red light periodically, you see that your melatonin rises just like it would for being in the dark. If you remember that curve, you're very insensitive to long wavelength or red light, the circadian system. But if you give people blue light, you begin to suppress melatonin. Now, if you look at cortisol, which has the opposite sort of rhythm, you see high cortisol rhythms, high cortisol levels under dim, red, and blue conditions during the daytime. As you would expect, under dim conditions, your cortisol levels drop in the middle of the night. But notice that red light and blue light elevate cortisol. That indicates that it is an alerting stimulus. So not only does you change your phase of your circadian rhythm with blue light, you can actually separate the alerting effects of light by changing the spectrum so that red light can be applied without affecting your melatonin rhythm. That becomes important, and we are working on R01 right now from NIH, specifically looking at night shift nurses and how they are affected by red light at night. Now, the other thing we can do is we can use scalp electrodes and we can measure EEG activity. And this is a study out of the early 90s of which what you see is this is a part of the spectrum that's generated from these measurements. And you can see that every time you turn on bright light, brain activity tends to increase. So you're more awake and conscious under light, non-pharmacological treatment to enhance performance. What we're able to do is make those same measurements, replicating them, but again looking at both red and blue light and how it affects the EEG activity. So we have two measures. One is alpha rhythms and one are beta. These are lower frequency, these are high frequencies. And so if you're more awake, your alpha levels should go down and your beta levels should go up. And indeed what you see is, in this case for red, giving red light at night reduces alpha levels, increases beta levels, as does blue light. So alerting effects are different than the circadian and training effects at night. Again, indicating that we might use spectrum as a way to enhance alertness without necessarily disrupting circadian rhythms. So here's similar data for the same experiment. We're now looking at the change over time during the nighttime in terms of the heart rate. And what you see is if you're sitting in dim light at night, your heart rate begins to drop. But if you give red light or blue light, there's a change, an increase in your heart rate for both red and blue. And the same thing happens on a performance test while you're trying to do go, no-go tests. You get worse performance sitting in the dim conditions. You get enhanced performance with both red and blue light in the nighttime. We're currently looking at exposure to red light during the day. We know that you're not suppressing melatonin, you're not phase shifting, but what we find consistently is that white light and red light during the day enhances alertness as measured, again, by this case, EEG activity and in terms of reaction times. So light during the day, so don't think about it just blue light, don't think about it just as nighttime. It looks like light exposure during the day can also enhance performance. And it looks like red light in particular turns out to be a very powerful way to do that. So in summary, these are your take-home messages. Solid state lighting has changed the world in terms of lighting, that's for sure. But what's important, I think, from a Navy operations point of view, that technology, yes, it's more energy efficient, you have degrees of freedom, but the bridge between research and application is much, much shorter now because the same technology you're doing in the laboratory is the same technology you're going to apply in practice. You throw away your filters and all the other things that we used to have to deal with. Now, the biophysics and the applications are much closer together. And remember too that light isn't just for vision anymore. Light also affects circadian rhythms. It also affects alertness. And I think this can be a powerful way of doing interventions if you understand the basic process. And I want to say that in all honesty, the Lighting Research Center, not just for myself, but it's a great honor to try to help as best we can with the translational research from the biophysics to this. So I'm extremely grateful to the Office of Naval Research and the U.S. Navy more broadly for allowing us the opportunity to try to bring some of these ideas to you. So I just thought I would end by talking about some of the current projects currently funded by the Office of Naval Research. One is dealing with hypoxia. It's a real risk. As you've moved, I guess, to OBOX, these things become problematic, and they're literally shutting down flight operations right now. Now, if you understand the biophysics, this is a paper that was published 7 years ago, and what you have here is the number of days as they climbed, I believe it was the Himalayas, and this black curve gives you the altitude and the O2 level. This axis over here, the other ordinate, gives you error scores for red-green confusions. Remember, there's two color channels, red, green, and yellow and blue. And what you see is that at sea level, before they climb and after they return, this is what we call normal sort of error rates that you get in the color test. And you notice that as they go to altitude, the red-green confusions stay pretty constant. But there's a spike in the yellow-blue region, and I can explain to you why we think that's true, because the metabolism in the retina is different for the different channels. Remember, it's not a homogeneous retinal platform. You have a red-green that is dominated by an avascular region in the very center of the fovea, and therefore less susceptible to hypoxia. And then the blue-yellow system is slightly displaced outward, high vasculature, and when you drop the O2, you begin to start to have confusion. So that's what we're exploiting. I was talking to Commander Oldie about this and perhaps getting this into cockpits and so on. Anyway, we have some ideas that we're exploring. We're not there yet. This is still 6.1, 6.2. This is a study that was also funded by ONR Global by Turner. This was her PhD thesis. And what she's looking at is caffeine. And I think the Navy runs on coffee. Is that true? And what you see is that if you have a placebo and you're now awake from 1900, staying awake, your performance just begins to deteriorate. This is a number of errors that you increase. Coffee works. Coffee keeps you active and alert. But I want to compare it to this pilot study we did. You get the same effects with light. So we say that light treatment is about equal to 2 cups of coffee without having to imbibe the coffee. Light can be a substitute. What we don't know, and nobody knows, what is the interaction between light and coffee? Is it additive? Is it synergistic in some way? Is it counterproductive? Those are the things that we're now trying to study with this ONR grant. The last one I'll talk about is, I showed you all these channel responses. I showed you one for circadian, I showed you one for brightness. We don't know what the spectral sensitivity is of alertness. So we're going to use, we had to develop this lighting system to be put in the fMRI. We're going to do some pilot data with EEG recordings, and then we're going to be collaborating with Cornell University with their fMRI apparatus to be able to see if we can locate in the brain where exactly these effects are occurring. And so this then just shows you how many channels we have, many degrees of freedom we have to control lighting applications. But we don't really know what alertness is at this point. We know that it has long wavelength sensitivity, we know it has a short wavelength sensitivity, but I don't know what the shape of that curve is or how it's done, and that's really our long-term goals. So I want to first of all acknowledge Dr. Mariana Figueroa. She was the young investigator that I referred to. She's now director of the Lighting Research Center, 3 R01s. Dr. John Bullough, who's been working primarily with the Federal Aviation Administration, doing, I think, really fabulous work at doing that translational work. And then these are the people we've worked with over the years that we've been doing. Sherry Parker, Sean Chautier, Chris Steele, some of these names I'm sure are familiar, Matt Keller, Colin Young, Brian Andrews Shitake. Is he here? Yes, he is. And Q, many of you know Q, who's now at ONR, I understand, and Igor, who was really the first person to support Marianne on her Young Investigator Award. So again, to repeat myself, I'm eternally grateful to everybody for allowing us the privilege to do that translational research from biophysics to applications. So thank you very much.